I'm going to start with some thoughts on energy efficiency in general, then I'll quickly move on to doing some empirical, two projects that I'm currently working on. This is very much work in progress, so feedback is very welcome. I had promised some theory to Simone, but then I realized that Tassos was here and Chuck was here, so probably my theory would not compete. I realized that Ulrich would be here tomorrow, so my empirics would not compete with one of his papers, so I'm presenting two papers today and see whether we can even out the thing. So anyway, let's start with energy efficiency. Energy efficiency is an interesting thing. We were talking over lunch about the fact that periodically it comes back. And it comes back especially when we run out of money. That's my impression. Why? Well, obviously it's a salient aspect from climate policy point of view because it reduces the need for energy in producing economic benefits. So, and on the other hand, it's relatively cheap because, as the OECD says, efficiency can enable economic growth, reduce emissions, and improve energy security. What more do you want? It's just amazing, right? You can do everything with that. And it seems to work out pretty well, at least if you look at the European Union and the United States. Basically what you get with energy efficiency is this decoupling of GDP, which is the pale top line, the pale blue line up there, and energy demand, which is the middle line, the darker one, is an index number, so it starts from 100, and as you see there is for the United States and Europe, there are declines in energy demand over time, given that energy efficiency decouples energy demand from GDP, energy intensity goes down, right? This is down to increases in energy efficiency. And it is such an interesting message to give, especially policymakers, like using the message that basically you don't have this trade-off quite as stringently anymore, that the OECD has even a new scenario that they came up with in the Energy Outlook, International Energy Outlook last year, where they look at what they call the efficient world scenario, and basically what they do is they consider all cost-effective technological options, and they assume that they're installed. And this gives us the difference between the blue line, which is the new policies scenario, which is already incorporating all the commitments in terms of current and future policies that are there, and the green line, which is this efficient world scenario. So it's amazing that you can see that emissions can decline just due to existing technology deployed and implemented, right? So it's fantastic. It doesn't quite work that way, right? Because if you look at developing countries, this is China, this is India, despite a significant drop, which is parallel, or almost parallel to, or even more probably than parallel to the one in Europe, and you see India and China go down with energy intensity, still GDP growth is so high that emissions still increase. Well, this is energy demand and hence maps into emissions, okay? So there is something that, despite the fact that we have all this technology that is cost effective, so it would pay by itself within the expected turnaround time, well the time limit that they assume depend on policies, but they are consistent with what experts tell them. Despite the fact that these things are cost effective, they're not implemented. So there's something that we don't quite understand about why these technologies are not adopted or implemented, and this gives rise to these kind of scenarios here for developing countries. So there is a lot more to be done about energy intensity, which is good for people like me who have been working on this and related topic for quite some time. There is a bit of a cottage industry on this. My take on potential aspects that need to further investigation would be, okay, so the literature is mostly partial economics, mostly micro, and mostly abstracting from economic environment, which, what I mean by this, the standard energy efficiency literature would look at what happens when there is an exogenous improvement in efficiency, what happens to demand, and then is there rebound, is there backfiring, this kind of stories. But all these stories tend to forget general equilibrium effects, because whenever you shock the system, there are all sorts of other things that happen. For example, very few people talk about the impact of energy efficiency on general equilibrium, and especially in general equilibrium when the economic environment is taken into account. For example, when you have multiple externalities, when you have overlapping policies, this kind of thing. So this kind of frontier is where we should do more work, and this is where I was starting to develop the model that I wanted to present here. And then it turned out that a lot of the assumptions that I wanted to make I wasn't sure about, because the empirical literature was not quite there. So then I got lost and I started doing empirics, right? So that's the end of the story. I can make it sound a bit more fascinating if you want, but this is what happened. I just got stuck in the empirics, and so this is what I'm going to present today. So what I'm going to talk about is that not only we need to look at this partial versus general equilibrium micro and macroeconomic environment, but we need more and more empirical support for the modeling assumptions. So for example, one of the things that I'm going to look at, the first thing that I'm going to look at is whether why is it that firms do not look at this margin in energy intensity or energy efficiency quite as much? So why are firms inefficient? So I'm not going to ask why firms are inefficient, but I'm going to ask whether firms are efficient. So is it true that we can assume that firms are efficient and they immediately take up every cost-effective opportunity, or cost-effective opportunity that comes their way? And in particular, I'm going to ask whether policy, which is in this case climate policies, this is the climate change levy in the UK, can affect this level of inefficiency that we observe in the data. And the second thing that I'm going to look at is what kind of instruments we have at our disposal, and whether we can measure innovation by trying to decoupling or paying attention to both the invention margin and the diffusion margin. Okay, so these are the two things that I'm going to look at today. So first, climate policy and efficiency of firms. I want to study I want to investigate whether firms are efficient or inefficient, so I need to try to use a tool that allows me, that takes me out of the standard production function assumption that the firms are all efficient, so what I observe in the data is an efficient production function. So what I do, I'm going to look into a stochastic frontier approach. But what I want to do is to also look at whether this inefficiency that I'm going to try to estimate can be influenced by policy. And there is not so much policy out there that is actually implemented. Obviously, there's the UETS, and in the UK, for example, we have the climate change levy. Since I'm UK-based and I have access to this data, I'm going to look at this. So the climate change levy was introduced in 2000 and started in 2001. And basically it's a tax on energy delivered to non-residential users. So everybody who's, in particular, we are looking at manufacturing, so all industrial producers will have to pay a tax. The tax is not on carbon because there is a different rate depending on the kilowatt hours produced in different using different energy sources. So if I click, whoops, I should have got, no, what did I do? Why is it going down instead of using the link? It's okay, there is somewhere, there is a link on, yes. So basically, different rates, unit tax over pence per kilowatt hour, which translate into an implicit carbon tax, which is the thing that you see here, out here. So it's not an energy tax that is constant, but it's more an implicit carbon tax that is different. But also it's not as easy from econometrically to try to estimate this thing, because on top of this climate change levy, the UK government decided that to protect industries exposed to international competition, they would allow sectors that were willing to negotiate with the government in terms of the commitments to climate change and emissions reduction to enter into what is called the climate change agreement, which which entails a number of reductions in emissions from the sector, but the firms within the sectors then get an 80% discount on the tax. And selection into this climate change agreement is not random, so we have to look at ways to correct our estimation for that. The good thing is that there is literature that argues convincingly that firms under climate change agreements were able to negotiate commitments that basically were not binding. So we actually, if we correct for the sample selection, we're actually getting closer to a causal estimation of the impact. And how I do this? I look at this through stochastic frontier, as I said, and I need to correct for sample selection. Stochastic frontier is relatively simple. What you see here, actually I probably should use the pointer. What you see here is the frontier. So there is a maximum amount of your output. In my case, it's going to be revenue or turnover. That is produced, this is logs, so this is a Cobb-Douglas production function with some inefficiency, which is, or some error that is normally distributed. But on top of this, we have that in the actual output level of the firms relative to this frontier, deviate from this frontier by a negative amount, which is the inefficiency level of the firm. And this inefficiency here, U, it depends on a bunch of control variables and my policy dummy, right? So if we assume that the model exhibits the scaling property, meaning that the fundamental variable here is U star, the distribution of inefficiency is common to the firms, but then basically from this distribution they get, for example, the management drawn. So they expect to have positive or negative impact depending if they pick the good or the bad manager. What happens is that depending on some environmental variables, their manager curve performs according to their drone or more or better or worse. So this scales up this fundamental distribution of quality of the management, if you wish, if you want to interpret it that way. We do a bit of assumption in terms of this being distributed within this being exponential, and then we estimate basically this thing here using the data. Before I can estimate this in a way that then tells me that the delta here, which is my dummy for the treatment, is actually causal, I need to control for the fact that this treatment is not random. So I have to apply Green's correction. Basically, if you remember, what did I do? If you remember your econometrics courses where you were using Ekman-Lambda, this is very similar, except that instead of estimating the probit model that gives you the probability of being treated and then correcting with what is called the Mills ratio, the estimated Mills ratio directly into the function, that wouldn't work here because this is not linear. So I need to, Green shows that I can do the same thing, but then I have to fit in the fitted probability of being treated. And you will see it come up. What do? I look at the annual respondent database. I add to it the capital stock database, which is always from the ARD but comes into different modules. And I look at all firms that have more than 250 employees plus a sample of the smaller ones. Depending on sectors, this is 100 or 250. Then I have information about fuel, and at the moment I am restricting myself to 4 sectors, which are the SIC code 15. This is food production, metal, and I don't remember. I can check on the paper if you're interested. But basically what I get, how much time do I have? Not much. What I get is this thing here, that across the 4 sectors, I get negative, yeah, I'm also answering my own question. I get consistently negative numbers up here. These numbers here are not immediately easy to interpret, but they're pretty large. So this is like a 70% drop in inefficiency. So if you're treated with a climate change levy, your inefficiency level, which might not be very big, but is reduced by 70%, which maps into something like between 11 and 17% of output of turnover, which actually incidentally maps quite well with some estimation that Raphael Kalel and others have done on, that is productivity and the UETS, but it's somewhat related to this. And then, okay, we do other things, but I want to get to the second thing. So basically what we see is that there is quite a bit of inefficiency here, and it's reduced by policy. So it's a good thing that firms are not efficient, but if you get them to focus their attention on things like carbon emissions, they might be paying attention. What does this entails in terms of modeling, I still haven't figured out, but this is what I'm looking for your comments to understand. The second thing so there's a lot of low-hanging fruit, that was the punchline here. The other thing is that once I know that these firms are inefficient, how can I get them to become more efficient in ways that are good from the policy point of view? In a sense, can I bias innovation somehow? And one way to do this would be to look at market-based policy instruments, but I didn't want to use the same example as before, so I'm looking at a different one here where I actually look at energy prices. So the argument being that if firms react to energy prices in a way that shows that they become relatively or that they increase more their efficiency along environmental dimensions, it means that I can bias innovation. There's a large literature on induced innovation, and what I'm dissatisfied with in this literature is that it looks either at the inputs, the R&D expenditure, or the outputs, the patenting, of only invention activities. Assuming that it's correlated with innovation, potentially is good, but this misses out completely on the adoption and process change and other kind of things. So what I do, I look at, again, at productivity analysis, and in particular now I apply data envelopment analysis, because it actually looks at the way firms behave. So it's not so much the question is not what is available out there as potential technology, as in the efficient world scenario, but it's actually what firms do. So what is actually implemented by firms. And then it's non-parametric, so I don't have to worry about whether it's Cobb-Douglas, whether it's in translog or whatnot. And then also allows me to not only to account for shifts in the frontier and movement close to the frontier, which is innovation and diffusion, but also allows me to measure these two components, because I'm going to use the efficiency indices here to compute Malquis productivity indices that can be split into technological change, which is the shift in the efficient frontier, and relative changes to the relevant frontier. And I'm almost done, actually. So how much time? 5 minutes, okay. So basically, what you do in DEA is you define an input pollution set, which in the two input case looks something like that. So this is your firm that uses this level of input 1 and this level of input 2. And if you want to use a radial measure whereby all inputs can be contracted by the same amount, you see what is the maximum contraction, or the contraction that I can apply to the inputs that I observe in the firm to get them to the frontier. And this contraction gives you a measure of the inefficiency of the firm. So how far away you are from the frontier along the ray. When we're talking about environmental issues, often these radial measures do not make much sense, because, for example, regulation might be affecting SO2 emissions, like in the US power plants, for example, but they don't necessarily affect, I don't know, water pollution from the heat exchangers, right? So it might make sense to look at no radial measures, and I do this by allowing, I have multiple inputs into that are actually, these are all energy relevant. They are not looking at water pollution here, but I have different pollutants, and I can measure the distance along this axis and along this axis, and then I have two distances, and I can use them independently, or I can average them, and somehow I get a measure of how environmentally efficient this firm is. Okay? As I said, once I have these indices here, these rows here, I can then put them together in a chain and compute Malquis productivity index, so how much this distance function change over time, which is useful mostly because I can immediately split this have this mean here into an efficiency change component and a technological change. So the technical change measures how much the frontier shifts out over time, and the efficiency change measures how much these distances to the frontier change over time relative to the appropriate frontier. Okay? Okay, this is fine. So then I apply this to US data this time, and I look at industry level data. Why do I do this? Because I'm trying to understand what is the aggregate effect on the whole sector. I'm not interested in entry or exit from the, for example, from the industry. So I just want to look at the frontier, and I look at metal production because it's a very mature industry, and there is not much in terms of technical change or innovation that is properly new products or product innovation. Is all about process innovation and management, which is the stuff that I was interested in to begin with. I have criteria pollutants, and I get them from the national emissions inventory. I'm going to just show you this, and then the second stage. So basically what I get is a measure of economic productivity or efficiency over time, and as you see, it's pretty flat, and then there is a bit of a bump in the 2000s. But when I look at the environmental productivity, this goes way up. Now, the numbers here are a bit difficult to believe, but this is why this is work in progress. I would like to have slightly smaller number and keep the same thing. So 5 is very high, but if I look at technical change, I get similar results, but twice as large, which is even more complicated from my point of view. And this is the efficiency change, and it's as you see, there is both technical change and efficiency change. So this is stuff that shifts the frontier out, and this is stuff that measures adoption of technology or diffusion of technology from laggards within the frontier, right? Okay, so then I want to understand whether changes in energy prices, and I'm done, can explain these changes, and basically I want to describe this picture econometrically. So there are energy prices and there are changes in productivity. Obviously I cannot claim any causality here, but I try just to look at the correlation, and I use lags and leads and stuff like that to argue my way around this. And what I get is that productivity change responds positively to higher expected energy prices. So these are this is T+2, but it's the price that the energy deflator that prevails in the following period that I observe. So there is the Malquist that goes up, the technological change that goes up. There is no big effect here in terms of economic impacts, but there is no significant change in environmental impacts. So this seems to be only about technological change. If I had time, I would show you also the lead and lags. But basically, what happens here is that what I would say, that then I do other things with the different prices, but I don't have time. So what I can conclude here is that on top of this inefficiency that I measured before, that exists and that explains possibly why firms are not immediately reacting to adopting efficient technologies without policy. Here I show that changes in the prices seem to lead firms to not only focus their attention, but also try to improve the productivity of the factor that has become more costly, relatively more costly. So this seems to support the idea that innovation is induced and biased in the sense of Higgs. And that's it.
Thanks a lot.